All right. Lastly, for our last question, we have to find the total response current of the circuit shown above, given that the initial capacitor voltage VC is equal to minus 6 volt and the initial inductive current is this. So before we go on, I want us to get the initial derivative of inductive current, because that's going to be our basis for this. So we know initial initial derivative of the inductive current, let me call that the I dt, that's at t equals 0. So at t is equal to 0, this source is just 2 exponential minus 2 times 0. That's this source. I'm applying KVL around this loop now. So by KVL, this is going to be 2 exponential minus 2 times 0, because t is equal to 0. Then you remember the current in this was given to be 1 ampere, so it's going to be minus. And let me give polarity. Let's assume the current is in this direction. So it's going to be minus and plus. Here is going to be minus, plus. Here is going to be minus plus, right? Sorry, plus minus rather, plus minus, plus minus, right? Because the current is actually flowing in this direction. Current enters a load from the positive and leaves from the negative. So if we have this established, this polarity established, the voltage drop across this is going to be minus, because we have a minus sign. Then here is going to be plus, and yes, here plus 5 times what's the current in this at the initial stage is times 1, right? That's voltage, sorry, resistance times current gives you that. Then how about this voltage? We don't know, so I'll give it VL. That's the inductor voltage. I don't know that for now. And how about the capacitor's voltage? You said initially the capacitor's voltage is minus 6 volts, so it's going to be plus minus 6 volts. Everything is equal to 0. So make VL subject formula. This is going to be minus 2 plus 5 plus VL minus 6 equals 0. So if you make VL subject formula, move this to the other side, this to the other side, this to the other side, you'll be left with VL is equal to minus 6 minus 2. That's going to give us minus 8 plus 5. That's going to give us 3 volts. So VL is equal to 3 volts. And remember, VL is equal to L times di by dt. So from here, what we'll get is that your di by dt, your 3 is equal to L is 1 times di by dt at the initial stage, because you know, remember, all the analysis we are doing so far is just for the initial stage. So from here you get that your di by dt for the initial stage is equal to 3 ampere per second, right? So that's it for now. This is just like a preamble, because we have to go back to the circuit and write out the differential equations that govern the circuit. So what's the differential equation that governs the circuit? We'll go around by KVL again. By KVL, here you are taking a general time t, not the initial time again. So by KVL, the voltage drop here is going to be minus 2 exponential minus 2t. That's the voltage drop here. Then if the current, inductor current I flows, you have that IL. We would have inductor current flow is going to be plus 5 times that I. I'll just, for simplicity, I'll just keep it I, or let me just put it IL, just to know that it's an inductor current, because they are in series. The same inductor current flows around, so that's why I'm using IL. So from there you have plus L di L by dt. That's the voltage drop across an inductor. If you remember, the voltage drop across an inductor is the inductance and the rate of change of current passing through that inductor. That's L di dt. Then from here you have plus the capacitor's voltage. Now, since we don't have a direct relation for the capacitor's voltage, you relate it to the current flowing through it. That would be equal to the integral of the current flowing through is divided by the capacitance, and that would be it. You equate to 0, right? So this equation, this is like an integral differential equation. And read what I just said: integral differential equation. It carries a derivative and an integral. So for you to like handle this kind of situation, you have to differentiate all through again. You differentiate here, 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 here with respect to t, so that you'll be able to, and this is with respect to t, sorry, and so that we'll be able to clear out this integral. So if we differentiate all through with respect to t, you get minus 2 times minus 2 exponential minus 2t plus 5 times derivative of IL with respect to time plus L is 1 already, so I'll just put 1 times the second derivative of IL with respect to time squared, then plus here if you differentiate an integral you just get IL divided by C. The value of C here is 1 over 4, that's 1 divided by 4. Differentiate 0, you get 0. So if you clear out this, is going to give you 4 exponential minus 2t plus 5 derivative of IL with respect to time, and then plus second derivative of IL with respect to time, then plus IL over 1 over 4, this gives you 4IL. Everything gets to 0. So we want to clear out this differential equation to make it look like a standard form differential equation. So we'll rewrite this. We'll take the highest derivative first, that's this, then plus the next highest derivative, that's 5 dIL by dt plus 4 times IL. Everything is equal to 0. Take this to the other side. Sorry, take this to the other side. You get minus 4 exponential minus 2t. Right? So we'll have this as our differential equation. So this is a standard differential equation with an initial condition. So first of all, if you are solving a question like this, you have to first of all find the unforced solution, right? Unforced solution. So for the unforced solution, we have the second derivative of IL with respect to time plus 5 times the derivative of IL with respect to time plus 4 times IL gives you 0. Because it's unforced, your right hand side is equal to 0. This is the characteristic. The characteristic equation of this is x squared plus 5x plus 4 equals to 0. So if this is the case, how do you get x? This is a quadratic equation. I trust you can all solve this. If you solve this quadratic equation, you end up with x is equal to minus 1 and minus 4. So our unforced solution, on first solution is usually regarded as I natural. In is going to give you let's take a constant k1 exponential minus t, that's minus 1t, then plus k2 exponential minus 4t. So this is our unforced or natural solution to this differential equation, where k1 and k2 are arbitrary constants. So how about the first solution? Solution, right? First solution to this differential equation. Remember, this is the second order differential equation. So how about the first solution? If you want to look at the first solution, you look at the nature of your right hand side. So the nature of the right hand side, let's assume a trial solution of I first in respect to time, or I first of time, is equal to a constant a exponential minus 2t. So substitute this into this differential equation. If this is this, then the derivative of I f with respect to t, if you differentiate it with respect to time, you get minus 2a exponential minus 2t, right? If you differentiate I f with respect to time, and then if you also differentiate again, that's the second time, that the derivative of I f squared, how do I write this? The second derivative of if with respect to time, you would get this to be 4a exponential minus 2t. I believe you are all following. This is just a simple derivative. You differentiate this once, you get this. You differentiate this twice, you get this. Or you differentiate this again to get this. So we substitute that into our differential equation, this very equation. So we substitute this expression into our differential equation. So in place of the second derivative of IL with respect to time, I'll write you have 4a exponential minus 2t, that's the second derivative with respect to time, plus in the place of that's 5 times the first derivative with respect to time is going to give you minus 2a exponential minus 2t, then plus 4 times in place of I here, I will write this a exponential minus 2t, and I will equate everything to my right hand side, which is 4 exponential minus 2t. So you can see that everything else, there is a common term here. If exponential minus 2t is here, is here, and is here, so if they cancel out by the way of dividing through by exponential minus 2t, you end up with 4a plus should actually be minus 5 times 2, that's 10a, then plus 4 times a, that's 4a again, is equal to minus 4. So here you get 4a plus 4a, 8a, then minus 10a, that's going to give you 2a, right? Minus 2a rather, is equal to minus 4. So at the end of the day, you get your a to be equal to 2. So our a is equal to 2. So our first solution, if of t, is going to be 2 exponential minus 2t in this case. So that's our first solution. So we have to like combine everything, because we know that our final solution, I of t, is equal to I natural of t plus I first of t. So that will be equal to I of t will be equal to I natural of t. Remember, is k1 exponential minus t plus k2 exponential minus 4t. That's the I natural. Then plus the I first is going to be 2 exponential minus 2t. So if you consider this equation, you have two more arbitrary constants to solve, but then the arbitrary constants to solve is not a problem, because we always have a way to solve that. So how do we solve this for this arbitrary constant k1 and k2? So it's going back to, from here we have that our I at t is equal to 0. That's the meaning of this I, 0 equals 1a, is equal to 1, right? Then our derivative of I with respect to t at t is equal to 0, that's what I just did here, and that is equal to 3 ampere per second. This is 3 ampere. All right, so if we have this, then we have everything we need in solving this. So we'll just substitute I at t is equal to 0 is equal to 1 into this general solution. You have I0 is equal to 1, right? And that is equal to, from here, is equal to k1 exponential 0 plus k2 exponential 0, because t is equal to 0 for this case, plus 2 exponential 0, right? So from here, we end up with k1 plus k2 is equal to 1. Call this equation 1. Why is this so? Because exponential 0 is 1, exponential 0 is 1. All right, sorry, it's going to give you minus 1, right? Because 2 will cross to this side to give you that. If you solve this, let me just make it simpler. 1 is equal to k1 plus k2 plus 2. So if you look for k1 and k2, k1 plus k2 would give you minus 1. So this is your first equation for finding k1 and k2. So we found k1 and k2. Sorry, we found a simultaneous equation. So we need a second simultaneous equation. So if you apply the derivative of I with respect to time at t is equal to 0, from here we differentiate this expression with respect to time. So from remember I is equal to k1 exponential minus t plus k2 exponential minus 4t, then plus 2 exponential minus 2t. So our derivative of I with respect to time, the I dt, if you differentiate this expression with respect to time, you know how to do differentiation. It's going to be giving minus k1 exponential minus t, then minus 4k2 exponential minus 4t, then minus 4 exponential minus 2t. This is just simple derivatives. So if you do this, remember you substitute at t equals 0, you substitute t is equal to 0, we have that di by dt is equal to 3, right, from here. So we have 3 to be equal to minus k1 exponential 0, because we are substituting t is equal to 0, minus 4 k2 exponential 0 minus 4 exponential 0, right? So this given 3 is equal to minus k1 minus 4 k2 minus 4, right? So we make everything subject formula. You have take k1 and k2 to the other side, or let's rearrange. 3 plus 4 is equal to minus k1 minus 4 k2. So at the end of the day, we have k1 plus k2 to be equal to minus 7, because this will give you plus 7, but if you divide all through by minus 1, you get minus 7. This 4k2, sorry, this 4k2. So you have this to be your second equation, equation 2. So if you have a second equation and equation 1, from equation 1, from 1, this is equation 1, we have that your k1 is equal to minus 1 minus k2. So substitute that into this place. You have minus 1 minus k2 plus 4k2 is equal to minus 7. So you make k2 surrogate formula, take this to the other side, you would get 4k2 minus k1, you would get, sorry, 4k2 minus k2, you get 3k2 would be equal to, this crossed into the other side, get minus 7 plus 1, right? All right, so that's equal to minus 6. So you get 3k2 to be equal to minus 6, and then from there you get that k2 to be equal to minus 2, right? If k2 is equal to minus 2, substitute that into this place. You have k1 plus k2 is equal to minus 1. That's k1. Instead of k2, I'll write minus 2 is equal to minus 1. So automatically k1 becomes, take it to the other side, 2 minus 1, that will give you 1. So we have our values for k1 and k2. So substitute that. Remember our equation solution, general solution is k1 exponential minus t, then plus k2 exponential minus 4t, then plus 2, is it 2 plus 2? Yes, 2 exponential minus 2t. So substitute k1 and k2, you have I to be equal to, k1 is just 1, so that's exponential minus t, then k2 is equal to, remember k2 is minus 2, so it's going to be minus 2 exponential minus 4t, then plus 2 exponential minus 2t. So this is the general solution for your integral differential equation, and that is it for this. You can take a snapshot. I would like you to comment your whatever your observation is. I know this is a little bit deep and it's based on your knowledge of differential equations. If you could solve differential equations from time, this should not be a challenge for you. But regardless, I think videos might be coming that would address differential equation, especially as it applies to electrical engineering in the future. So stay tuned for more video. If you've not subscribed to this channel, this is the right time to do that, and I'll see you in the next video. Have a nice day.